Welcome. This is our second webinar in the series on heliophysics education and the heliophysics big year themes in particular, and math. So our speaker for the series, which goes from November 2023 to December 2024, is featuring Dr. Sten Odenwald. And I'm going to share my screen just to get us started and introduce Sten, and then he can take it away. So the heliophysics big year was developed by Communications, and they have suggested that there are themes that can be addressed throughout the year because of all the events happening this year. So this month is about citizen science. So you'll learn all about the citizen science that has enabled heliophysics discoveries, including types of auroras and other things. You'll learn about some of the missions that are studying the sun and the heliosphere. And this connects with our NASA HEATS framework for heliophysics education and NGSS standards. So Dr. Sten Odenwald is offering these monthly webinars. He's a member of the NASA HEAT team at Goddard. He has a bachelor's degree in astronomy from Berkeley and master's and PhD degrees from Harvard using infrared astronomy to investigate star-forming activity in the nuclear regions of the Milky Way galaxy. He's had many positions over the years at NASA, including as well as other places, including the Space Science Division of the Naval Research Laboratory, being with NASA's Cosmic Background Explorer mission, Director of Education and Public Outreach for NASA Image, a mission from 1997 to 2002, Director of NASA Space Math, which is still up. You can go to Space Math at NASA. Since 2005, Heliophysics Education Activation Team is his current position. And he's developing a lot of interesting resources. In addition to numerous technical articles, he's also published over a dozen books for the general public, including the 23rd Cycle, Learning to Live with a Stormy Star, that would be our sun, Patterns in the Void, Why Nothing is Important, Interstellar Travel, An Astronomical Perspective, and Exploring the Heliosphere from the Sun's Core to the Interstellar Void. I highly recommend these books. They're great fun, easy reading in most cases, but a lot of depth. Dr. Odenwald has received numerous awards for his public education and writing activities, including the 1999 NASA Goddard Award of Excellence in Outreach and the 2000 and 2009 AAS Solar Physics Division Popular Science Writing Awards. So we have a public folder, and I'll put these slides up again at the end, where you can see slide decks from completed webinars and view recordings or listen to them of completed webinars. Then coming up in January, mark your calendars, January 16th, and this will be from agriculture to economics, how the sun touches all parts of our lives. So I'm going to stop sharing so Sten can share. Welcome, Sten. Take it away.
Okay, thank you, Hillary. Let me get my ducks in order here. Okay. Let's see. All right, excellent. Well, thank you all for taking the time to participate in this session. I have a number of things to share with you. First of all, what is heliophysics? This is the heliophysics big year, as we call it. Well, heliophysics is a discipline in astronomy and in physics that deals with basically everything from what's going on in the core of the sun to what's going on where solar influences interact with the interstellar medium, and that's way out where the Voyager spacecraft are currently living. So it studies the physics of nuclear fusion at the core of the sun. It studies issues of why the surface of the sun is so magnetically active. And it also discusses in some detail how it is that the sun influences the planets that orbit it. And sometimes those influences are really good. Like it's really nice to have a star that has a lot of gravity to keep us in a stable orbit. But when the sun is magnetically active, well, then it's no longer a good friend of ours because it's throwing out plasma that interacts with the Earth's magnetic field and causes aurora and can really do a lot of other rather mischievous things. The interesting thing is that if the sun did not have a magnetic field, it would look very boring. The surface would not have any character whatsoever. There would be no sunspots. All we would see would be a bunch of convection cells, like we would see in a pot of boiling oatmeal. Kind of boring. So it's good that we have magnetic fields because they give stars their individual characteristics. Well, okay, enough for highlighting stars. The Heliophysics Big Year has a kind of a timeline that was set by the annular eclipse, which we saw in October. The middle of this period is the total solar eclipse, which is in April 2024. And then finally, December in 2024, we have the close encounter of the Parker Solar Probe with the sun. It'll get the closest that any human instrument has ever reached the solar surface. It'll be within about 6 million kilometers, but in terms of solar system distances, that's like a next door neighbor. The big year themes there are 14 of them, I guess there are. We've done October and November, and this December theme is going to be about citizen science. So I'm going to give you a little bit of a worm's eye view, not only of citizen science at NASA in general, but the particular projects that are involved with the sun specifically. And then, of course, as we go through the rest of the Heliophysics Big Year, in that right-hand column, you'll see other themes that we're going to cover. Yeah, I know, February, we're going to talk about fashion. I'll let your imagination run wild on that subject. Performance art in June. Well, there are some interesting performance art issues that have to do with the sun. And of course, my favorite in November is going to be bonus science. Well, you know, anything you do in science is a bonus, always something new every day. So that'll be a really fun talk to put together. And NASA has 3 big questions that organize its research, at least nowadays. What causes the sun to vary? How do the Earth and the heliosphere respond to this variation? And what are the impacts on humanity? Those are the big questions that have to do with heliophysics. We have other big questions that cover the other disciplines like astrophysics and planetary science and earth science. But these are the ones that organize heliophysics and heliophysics education. In the education arena, we break these big questions down into sub-questions that are more amenable to mapping into the national science standards, and we provide a lot of connectivity into the science standards through the framework for heliophysics education, which we've developed over the last year. Okay, citizen science. This is a fun activity. This is the kind of activity that you do when you go outside and look around you. You're gathering data about the world. Your brain uses that data to form a model of the world. And then for the next few seconds, you get to interact with that world. And it's been a process going on since the beginning of organic life on the planet. Citizen science, the way we talk about it now, is individuals joining large groups to analyze data or to gather new data and to coordinate that data with a principal investigator scientist who's looking to collect particular kinds of data in order to further some theoretical ideas or hypotheses that they might have that advance science. This is not kid stuff. This is real serious science being done by, you know, your grandparents, your mother and father, you know, people with an average interest and knowledge of the world, but a real passion to really understand more of the world than just what they read in the newspapers. Citizen scientists are very aggressive with data gathering. Ask any ornithologist or bird watcher. You know, they go out into the middle of nowhere and stand in a swamp and count birds. And in heliophysics, we have a number of programs. We've got about 14 programs where citizen scientists can basically do the same kinds of things with heliophysics data that's gathered by satellites. we're living in a time where heliophysics data that we're gathering about the sun and the environment of the Earth and space, it is literally a fire hose. I mean, a scientist can't look at all of this data and understand it coherently. What we need is a lot of help. We would prefer using humans to do that help, but if the database is too big, we have to use artificial intelligence to give us some hints as to what corners of the data to look at for interesting patterns and correlations. So citizen scientists get to look at this data too, and because they're humans and because humans are really good at pattern recognition, they can do miraculous things that computer programming can't do. Well, at least not yet. The projects about the sun and citizen science, well, I'm going to go through a kind of a list of them, but I'm not going to delve with any of them in any particular detail because we don't really have time. Sun Grazer, Solar Active Region Spotter, Solar Jet Hunter, Sun Sketcher, Mega Movie, Radio Jove, and Kate. These are all programs that look at aspects of the sun's corona, active regions on the sun. Mega Movie is a program which deploys cameras along the path of totality and basically takes images of a total solar eclipse at the point where the camera is located, films the entire event. And then what happens after the eclipse is over is that all of these individual movies are combined together. Instead of giving you a 2-minute view of what the corona is doing, the combined movie can span something like 20 to 30 minutes, which is the time it takes for a complete eclipse from start to finish over the geographic area. So with this kind of a data, you get to not only gather it yourself as a citizen scientist that's registered with the program, but you also have the satisfaction of it at the end, seeing what the corona looks like and what it's doing, how it's gyrating over the span of 30 minutes instead of a couple of minutes, which is what you're going to get to see during a total solar eclipse. Sun Sketcher is all about sketching what the corona looks like. This is a technique that goes back several hundred years. Before the advent of photography, the only thing astronomers could do during that 3 or 4 minutes of seeing the corona was hurry up and sketch it as best they could. Towards the end, they realized that they were no artists, and so towards the late 1800s, they actually got professional artists to see what the corona looked like, because they can see details that the typical person can't, plus they can remember details a lot better. So they used to turn out sketches of the corona that were almost photographic in quality. And in fact, it turns out that for that technology, photographs were very poor in capturing fine detail that's very obvious to the human eye. So for the entire 1800s, sketching was an extremely important way of gathering important data about the corona. Sun Sketcher is sort of a retro version of that, where we're going to let the average person experience what the corona looks like and then try to sketch what it looks like as best they can, and then submit that to a database, which then astronomers can look over and see if there are any features that seem to be missing from the photographic data that they've acquired. So it's kind of a cool project. Radio Jove looks for radio flares and outbursts of radio energy from the surface of the sun. You build your own radio telescope from a kit that's provided. And then you basically monitor the sun, not just during the eclipse, but for as long as you care to be part of the program. I mean, every day when the sun is up over the horizon, you monitor it for radio burst activity, and you provide this data to the Radio Jove scientists, who then can use that to figure out how the bursts are related to the various optical things that you're seeing from other observatories, and for instance, like the Solar Dynamics Observatory in space. You learn a lot by collaborating across the wavelength disciplines when you want to study the sun. Sun Grazer is a really cool project that's been going on for over 20 years now. It turns out that the SOHO satellite is an instrument that basically eclipses the sun so you can see the corona, but it turns out you can also see comets falling into the sun. They have discovered over many thousands of these comets, and the Sun Grazer project has essentially citizen scientists poring over images of the sun's corona, looking for hints of a comet. And then they record it on that image and then forward that information to the PI. It turns out that these comets are extremely exciting to watch and to study, and provide us with an important insight into what the smaller objects in the solar system look like and how often they fall into the sun, which is an important feature of producing some of the corona that you see. Some of the corona that you see is actually dust from the zodiacal light in the solar system, and those are dust grains falling into the sun. So dust and the corona are kind of intimately connected, and comets are also connected to all of that as sources of interplanetary dust. Other projects that we have Aurorasaurus, which studies aurora. Here you have your cell phone app, and whenever you see an aurora in the northern hemisphere or in the southern, you make a record of that and forward it to the Aurorasaurus archive. The idea there is that scientists make predictions about where you should be seeing aurora based on these very complicated theoretical models of how plasmas work and how energy flows. And the question is, how good are those predictions compared to what people actually see on the ground? If you're seeing aurora where the prediction says there shouldn't be one, well, that's great information for the theory, because then you have to ask the theory, well, why didn't you predict that there would be an aurora over there that somebody saw? And so that advances the details in the model and our understanding of exactly how aurora are produced in some considerable detail. HAMSCI is a really cool program, and it's related to the DEB initiative. Here you're making radio measurements of the ionosphere, and it turns out, for instance, during a total solar eclipse, the ionization of the ionosphere changes because there's no longer ultraviolet light from the sun available to it. And so the reflective properties of the ionosphere for radio waves changes, and you have ham radio stations separated by several thousand kilometers. They will detect changes in the ionosphere reflectivity. And this gives you important information about, well, how rapidly the ionosphere recovers once the source of ionization is removed, which is the ultraviolet light. And it also gives you information about density and temperature and other things like that. So you learn an awful lot. And nobody thought that a change in the ionosphere could happen that quickly during a total solar eclipse. But in fact, substantial changes of the ionosphere do happen from literally minute-to-minute timescales. So we're learning a lot about, how that all works just by studying radio emissions or reflectivity. Soundscapes is a really cool project where you basically have an audio system listening to the environment around you during the time of a total solar eclipse. Well, it turns out that animals react to the sudden darkness in the middle of the day, and Soundscapes is going to record the change in environmental noise from birds chirping or frogs croaking or whatever the current animal biosphere is like at the location that you're at. And so this is a really interesting way of sort of confirming an older idea that somehow animals respond very quickly to a total solar eclipse by basically feeling like it's all of a sudden day has turned into night, and so they have to prepare for being nighttime behaviors. Birds stop chirping, and the carnivores start coming out of their lairs and looking for food. And then 2 minutes later, oh, okay, eclipse is over, it's daylight, I got to get back to my lair. Oops, big mistake. And there are other projects too like that are going to be very interesting around the total solar eclipse and are sort of driven by that. Many of these projects are also operational when there isn't a total solar eclipse. So they're going to be very, very interesting to participate in. And if you want to, this page gives you essentially the links to the main pages of these projects. I'm not going to dwell on them very long, because when you look at the PowerPoint yourself, you can call up this page, and at your leisure, you can, click on the links and go and see if you're interested in that particular project or not. Well, today what I'd like to talk about are aurora. Aurora are an aspect of heliophysics and space weather that basically hit you in the face like a pie. They're the most accessible aspects of space weather because if you live in the northern latitudes, you see them, from September through March when the skies are dark and long and the sun is active at one level or another. So we've known about aurora since, goes back thousands of years. Earliest aurora account dates from the 2nd century BCE. So people have seen these for a long time. They've developed a lot of mythology about what they are. What I'm going to do is sort of give you a step-by-step explanation as best I can of how they happen. The whole process starts, as many things do, at the surface of the sun. The sun's surface is magnetic. These magnetic fields can combine to form very large structures, and sometimes those structures can be ejected from the sun. They have enough energy to achieve the escape velocity, and so they're launched into space. We call them coronal mass ejections, or more properly, interplanetary coronal mass ejections, because they are now interplanetary objects traveling through interplanetary space. While they're near the sun, they are just simply called coronal mass ejections. So a little bit of the nomenclature that is kind of interesting. At the same time that the sun is producing these CMEs, it's also producing something called the solar wind, but that's a subject for a future talk. This is a flow of particles out from the sun at typically about 200 to 400 kilometers per second. So it's a pretty stiff, rapid flow of particles. These expand out through interplanetary space all the way to the orbit of Pluto and beyond. The coronal mass ejections, when they're launched, they slam into this expanding wind, sometimes at speeds of several thousand kilometers per second. We're talking millions of miles an hour. The largest coronal mass ejections are also the fastest ones. They can travel from the sun to the orbit of the Earth in something like 15 to 17 hours. So as soon as you see one of these things launched from the sun, within 15 to 20 hours, you will have some kind of an effect here on Earth if the CME happens to be directed in our direction. Now, to understand this whole idea of Earth living in a shooting gallery, if you were standing on the surface of the sun, first of all, you'd be ionized, which is not very pleasant, I'm told. But looking out into the sky, the Earth would appear to be about the size of a quarter. That's the magnetic field of the Earth surrounding the Earth has a size that would be apparent to about the size of a quarter standing on the surface of the sun. So if a coronal mass ejection is going to be launched that affects the Earth, it has to be launched so that it is directed towards that quarter that you're holding up in the sky. Now, that doesn't happen very often. But the thing is that coronal mass ejections, by the time they get to the orbit of the Earth, they have expanded into something that's like a wall of plasma over 1 million miles across. So it's easy to hit the barn with a rifle, and it's very easy to hit the Earth with in a shooting gallery where you have coronal mass ejections that are that big. So typically during the time when we have sunspot maximum, you could expect to see one of these very large coronal mass ejections literally every few weeks. 2 to 3 weeks is a typical interval between these things that are directed at the Earth. The rest of the time, the sun is producing these things, on a daily or semi-daily basis, and they're shooting off in all kinds of other directions at this time. But once every couple of weeks, you'll have one directed towards the Earth, and then, quite frankly, all hell breaks loose. When this wall of plasma and magnetic field reaches the Earth's magnetic field, a very dynamic interaction happens. Here's an example, a model. This is a mathematical model. This is not an artist rendition of what the Earth's magnetic field looks like in the presence of the solar wind. which is has a magnetic field and also is weakly charged, but also where there is a fairly weak coronal mass ejection passing by, and that's all that light green stuff that you see on the left side of the screen. This coronal mass ejection, when it hits the Earth's magnetic field, it compresses the field on the day side of the Earth. On this model, the sun is located off to the left-hand edge of the picture. So the wind is flowing from the left to the right, as is the coronal mass ejection. So in some sense, the magnetic field of the Earth gets pushed back, and the field kind of resembles what we call a windsock. You might see those at airports. You know, they tell you the direction of the wind across the tarmac. Well, the magnetic field of the Earth also gets pulled back and points in the opposite direction of the sun, according to the same physics. So what happens is that the main impact happens at the magnetic field point that's directly aligned with the sun. In fact, if you were standing on the Earth, it would be exactly noontime on the Earth, okay? Because in this picture, the right half of the Earth is in darkness because it's nighttime, and the left half of the Earth's disk that you see is in daytime. And basically, we're looking at a noontime slice as we're looking out towards the left-hand edge of this picture if we were standing on the Earth. And so one thing that happens that's very interesting is that some of the particles from the CME can actually infiltrate down into the polar regions on the day side of the Earth. You see, if you look at, let's see if I can use this pointer. If you look at this region here, it looks like a funnel, all right? It's a magnetic funnel. And the particles from the wind can actually flow down into these polar funnels. They're called clefts. And you would think, okay, that's really great, because now I understand that, you know, aurora are produced when particles from the sun interact with the atmosphere of the Earth. Well, that statement is only 50% correct, because the aurora that would be produced by particles coming directly from the sun and going directly into the Earth's atmosphere would be those coming from the day side half of this picture. And of course, you don't see spectacular aurora in the daytime because they're too faint. The only aurora that you really see are the ones in the nighttime. And the way those are produced is a really interesting process. As you see, this tail of magnetism from the Earth is pulled way, way back into space. It extends beyond the orbit of the moon. That produces a lot of tension in the magnetic field to be stretched that badly by the flowing particles. So what happens is that the field begins to break up into blobs, and you can see one of these blobs here, but it also pinches together in the region that's closest to the Earth. That pinching becomes so extreme that eventually a process called magnetic reconnection occurs, and this releases an enormous amount of magnetic energy, and that energy goes into accelerating particles that are already present. There are plenty of charged particles present in this entire volume of space. We have the Van Allen radiation belts that are close in, and then further out, we have various plasma populations that are existing, that are spiraling around the magnetic field, waiting for something interesting to happen. When this magnetic reconnection event occurs, magnetic energy is pumped into these particles, causing them to become very high energy particles, but they're still trapped by the magnetic fields that they happen to be sitting on. And so these particles flow into the polar regions of the Earth from the nighttime area of the Earth. You see, this direction here. If you were standing on the Earth looking out, this would be midnight. So if you stand on the surface of the Earth and look directly up into the zenith where you're located at midnight, you're basically looking right down the tail of Earth's magnetic field. And these lines of magnetic force are connecting into the poles of the Earth. And this is where these high energy particles are now flowing. And when they get into the Earth's atmosphere near the poles, that's when they produce the spectacular aurora that you see. Okay. These aurora are not produced by particles coming directly from the sun and going into the poles on the daytime. They're produced by particles that are trapped in the Earth's magnetic field in the nighttime that have been accelerated back into the poles of the Earth. So it's a kind of an interesting process. We're learning a lot about it with satellites like Themis and MMS. It's exciting that these theoretical ideas for how this works that was produced in the 1950s is now being confirmed by satellite data that we can gather right at the site of where these reconnection events are happening. As I say, the magnetic reconnection that goes on in the Earth's magnetic field causes particles to be accelerated. These particles come usually in clumps or in clouds, and they flow into the poles of the Earth. And this is a computed model of what that looks like. The theoretical physicists can look at and say instantly what's sort of going on. But the takeaway from this is that these very lumpy clumps of plasma, when they flow into the poles of the Earth, they produce an ever-changing auroral curtain and a variety of effects that you see on the ground as the aurora change from minute to minute, as these particles arrive in their various clumps along the magnetic field lines. So we're beginning to sort of understand really how this all happens, and it's an extremely amazing process. And it's very different than what people thought back in the 1800s. It's just amazing when you take a step back and see just how far our understanding has come. There's a lot of detail that we don't really know too well, though. Our theoretical models provide extremely high resolution views of all the physical phenomena that are going on. Unfortunately, our satellites can't be everywhere all at once. And so it's like you're trying to understand what's going on in a trillion cubic mile volume with only a couple of spacecraft that can only see what's going on right where they're located. And it's amazing that we're able to sort of knit a picture together that connects our high resolution theoretical models with the very sparse data that we actually collect in space. This only works for one fundamental reason, and I don't want to wax too philosophical, but this only works because our universe is an ordered, organized system with physical laws that you can take to the bank and an enormous amount of built-in regularity for how things work. If things were random in the world, we could never model anything, that wasn't, 6 inches beyond our face. And luckily, the world doesn't look like that. And arguably, if the world looked more like that, we wouldn't be here to marvel at its randomness, because we wouldn't be here either. Humans require an awful lot of regular chemistry that happens over and over again for millions of years the same way in order for us to exist. And so the same principle applies when we're extrapolating our mathematical models, which are based on nature's regularity, to match it up with actual data that we take. At some degree, it's exciting that they can match up as well as they do. And that's a thing that scientists always marvel at every single time one of their predictions matches up with an actual observation. But it's also amazing that we can so sparsely sample the world and yet still create a coherent model of what's going on, beyond our noses, quite literally. So anyway, that's enough of philosophy. I'll put my scientist hat back on and get back into the topic at hand. Right, the energetic particles that stream in from these reconnection events in the magnetic tail of the Earth, they collide with the oxygen and nitrogen and hydrogen atoms that are in the upper atmosphere and the stratosphere. And those collisions are at very high energy. And they allow the electrons within those atoms to get excited and then to become de-excited, because that's what excited atoms do. They jump up to a higher energy level when they get hit by something, and then they, over time, fall back to a lower energy level and give up a photon of light. It turns out that in oxygen and nitrogen atoms and in hydrogen atoms, those photons of light have specific colors. For instance, hydrogen lines tend to look red because there's a particular transition in the hydrogen atom that gets stimulated to produce a red color. For oxygen, we have a more greenish tinge to things, although some of the lines in nitrogen atoms also produce green light. It's oxygen that produces the most intense green light. And then finally, for nitrogen, it can be basically produce the bluish tinges that you see from here, from now and then. The other thing that's interesting is that the motions that you see in aurora are complements of one very important phenomenon, and that is that if the light is produced too slowly by these atoms, the image will be smoothed out over time, so you won't really see very rapid changes. But if it takes only a very short time for the atom to become de-excited, that means that your time resolution of the phenomenon becomes very short. So you can actually start to see these actual changes in the shapes and positions of the aurora over time. It turns out oxygen atoms have the best combination of these things. So consequently, you tend to see aurora in the green light changing in a recognizable way as you're standing there watching, from minute to minute. Nitrogen apparently has an even shorter time scale, and so sometimes you can see blue features changing even more rapidly. Hydrogen is produced at a higher altitude, takes a longer time to de-excite compared to oxygen, and so you'll generally see a red glow that really doesn't change a whole lot over minutes to several minutes. So that's an example of how aurora are produced. To actually observe them, you have to be in special places that are located close to the magnetic poles of the Earth. We like to characterize the severity of these magnetic changes, which presage auroral events according to what's called a KP index. It's just a measure of how variable Earth's magnetic field is in a given location. And so here we have a scale. KP of 8 is a really strong storm, even a superstorm, and you get maybe one or two of these every sunspot cycle. Storms that are at the level of about a KP of 5, you'll get them maybe once a month or so, once every 3 weeks or so. KP of 6 or 7 is more intermediate. You might have to wait a couple of months to see things that are that strong during sunspot maximum. For the others, KP of 1 to 3, that's a typical bad hair day for the sun. You'll see things like that almost on a daily basis. That's typically where the sun likes to bubble and boil in the way it affects Earth's magnetic field through these various influences. These influences can include irregularities in the solar wind itself. It can include very weak coronal mass ejections of the wrong polarity, and that's a subject I really don't want to get into. And it can also involve coronal holes and high-speed streams coming from those things. They typically produce KP of 1 to 3 events. So, the best way to know whether or not you should go out and look for an aurora is you should probably look at some space weather service. NOAA has one at this URL, Space Weather Prediction Center, and they provide daily predictions and forecasts of how active the Earth's magnetic field is, radiation fields, KP indices, optical variation, and things like that. So that's a good place to go. There's also spaceweather.com, which is a very entertaining place to go. Not only do they talk about space weather, but they also give you the last 24 hours worth of bolides that have entered the atmosphere and show you what the orbits look like for those. And that's always fun to look at, especially during a meteor shower. Right, coronal mass ejections, they produce variability in Earth's magnetic field, and that's what magnetic observatories like to monitor with very sensitive devices called magnetometers. But you could actually build one of these yourselves for under $50. If you'd like to learn more about that, I have a book called DIY Magnetometers that you can find, or you can contact me via email and I can sort of turn you on to how to build these devices. NASA is producing a series of booklets on how to build things like this as well. The top red graph is from a professional magnetic observatory, and the green bar shows where identifiable magnetic storms occurred. And the bottom three traces, the blue, green, and black, are from homemade magnetometers. So you can see they're pretty good at picking up many of the events that professional, $100,000 magnetometers are routinely seeing. And even on a daily basis and an hourly basis, there are some very interesting phenomena that go on that you can also monitor with these kinds of very inexpensive instruments. They basically consist of a suspended magnet that you measure with a Hall sensor, and the Hall sensor goes into an amplifier that measures differences in position. You also have a digital to analog interface to the computer and a software package that lets you plot in real time how that magnet is moving around. And the magnet is going to follow the Earth's magnetic field locally. So you're basically doing a one-for-one detection of whatever the Earth's magnetic field is doing, where you have this device and you're monitoring its changes. So that's sort of the basic idea. So yeah, there are some interesting opportunities also to explore how mathematics is connected with all of these things. Space Math at NASA is a resource that we developed back in 1905. 1905? No, make that 2005. I'm not quite that old. I mean, there were dinosaurs around when I was born, but most of them were extinct. But anyway, yeah, I mean, it also has a search engine feature, so you can very quickly search through 1,000 math problems and find ones on a topic of interest to you, whether it's aurora or black holes, and the level of math that you're willing to be exposed to as either a student or as a teacher, if you want to print these out and distribute them while you're taking attendance. Or whatever your particular need is. You can even, copy and adapt these things, to your own purposes. They're very flexible. They're only one page long with an answer key on the back, so you can't really go wrong. What I'd like to cover today is basically a simple question: how high up are aurora? And also related questions: do they ever reach the ground? And also, can you ever hear one? These are questions that come up as soon as you start talking about aurora as a physical thing, and standing there watching them, you start wondering, well, where are they? How high up? Can I actually hear one of these things? Things like that. So what we're going to do is we're going to cover this subject in a couple of different ways. First of all, in the 1800s, early 1900s, a Norwegian astronomer basically went to the Arctic with photographic gear, and he set up a pair of cameras located some 100 yards or 1,000 meters apart, and took photographs of the same aurora from two different vantage points and compared the position of the aurora against the background stars. This is the same principle that you would use if you were to at arm's length, hold your thumb up at arm's length, and then to look at your thumb against the background of your bookcases with one eye open and then the opposite eye open, and you'll see that the thumb shifts back and forth relative to the background. Well, Carl Stormer thought that you could apply the same principle to figuring out how far away these aurora were just by using this, what's called the parallax method. And what I'm going to do is show you how this works. We're going to do this sort of in three ways. An introductory way for the younger learners, middle-aged learner at grades 6 to 8, and then advanced at grades 9 through 12 or more. So you get a flair for, or a sense for how the approach changes and sort of gives you different information depending on literally how much math you're willing to put into the problem. The simplest thing to do is setting up a problem like this, is that suppose you had two observers located 30 kilometers apart. That's the length of A to B. Observer A measures the aurora what that angle is from the base up in the direction of the aurora and says it's about 53 degrees, the angle A. Observer B says that that angle is 114 degrees. Well, he's actually measuring the complement of that, but we'll mark it as angle B is 114 degrees. And so with this information that the distance from A to B is 30 kilometers and that those two angles are what they are, you can draw a scale drawing of this, all right, using a millimeter ruler to represent, 3 millimeters equals a kilometer, and then using a protractor to measure the two angles. And what you'll get is the intersection point, which I labeled the aurora. And then you can just do the drop down vertical to get the height of the aurora and measure that using your scale drawing. So that's a simple way to do this and convert this into a problem of creating a scale drawing where the student just needs to be able to use a ruler, create a scale of ruler measure to physical measure, and then to use a protractor to measure the two angles. So very straightforward, and you get an answer. These are sort of made up numbers of about 100 kilometers, but it's not a bad number because typically aurora are about 100 kilometers up, give or take. The next approach involves using the parallax method in a bit more detail. Here we have two photographs of the same aurora. In the actual photograph, not only do you see the aurora, but you also see some background stars, which unfortunately don't show up quite so well in this. This pair of photographs was taken by Ryuho Kotoka in Tokyo. He used a pair of Nikon cameras and set things up to make the measurement. And the arrows point to the positions of the same star seen in these two photos. Well, you can all automatically see that the aurora placed relative to the point of those arrows has changed a little bit. Now, what you can do is blink these two back and forth, and I'm going to do that here. And what you'll see is the actual motion of the aurora. I've tried to center that star as well as I could, but you'll see that the aurora does actually shift just a little bit in position. Now what we can do is we can be a little bit more mathematical about this. We know what the field of view of this image is. It was about 26 times the diameter of the full moon across, which works out to be about 13 degrees from edge to edge in the horizontal direction. And we can use that along with a millimeter ruler to essentially set the scale of this image in degrees per millimeter. If we measure the displacement of a particular feature, okay, I've selected, here is where the star is, and I've selected a feature in the aurora that seemed to be about the same in both images. If you measure that distance, which is that yellow line, in millimeters, you can convert that into the angular measure using the scale of the image. And for the length of this A image, you get about 2 degrees. And for the length of the B image, which is on the right, you get about 3 degrees. So the difference in angle, that is the shift, is 1 degree between these two images. That's called the parallax shift. So from where you're located, and in this particular case, the aurora is almost straight up because it's one of these coronal aurora events. You can measure that the parallax displacement is about 1 degree between these two camera measurements. Now, on the diagram, the triangle is the aurora, and that star is, well, that's the star. So in sort of this cartoon sketch, we have vantage point A is looking in one direction, seeing the aurora, and vantage point B is looking in a slightly different direction and seeing the same aurora feature. So the angle difference, B minus A, is 1 degree, and the distance between A and B, in this case, is 2 kilometers. So I just set that up as a typical number. So with a little bit of math, the distance to the aurora from this parallax measure is basically 2 kilometers times 57.3 degrees divided by 1 degree. That's the conversion between radians and angle. 1 radian is 57.3 degrees. And basically, this formula is 2 kilometers times the shift in radians is the distance. So this gives you about 114 kilometers for this particular diagram. So this is an equivalent way of doing it, but the thing is, we're not quite finished with the problem yet, because what we've measured from the parallax is the distance from the observers to where the aurora is as 114 kilometers. But that doesn't give us the height. That gives us the hypotenuse of a triangle, of which the height is basically the vertical side. So to get the vertical side, we have to basically multiply the hypotenuse, 114 kilometers, times the sine of this angle that we're measuring. Each of the parallax cameras measures about a 60-degree elevation angle for that particular spot in the aurora. And so when you do the math, it's basically 114 times the sine of that angle. And so you get an answer of about 99 kilometers is the height of the aurora feature that we were looking at. So that's method number 2 for getting at the height of an aurora that uses the parallax method. The third way we can do it, well, this involves a little bit of advanced trig. The basic idea is that we have 2 observers. We're looking at the same feature. And like the previous method, they measure the angles, and then they work out essentially what the height is. But the approach is a little bit different, because as you see in this figure, observer A is looking at the aurora and has one particular triangle that they're using to spot the height. And observer B is using another triangle, which has the same height as a common element, but basically has a different base length and a different base angle. So combining this information is a little bit tricky, but it leads to essentially the same result. Here's how we do it. Well, first of all, the simplest geometry is going to occur if observers A and B are lined up with what they think is the base of where the aurora is. If you were standing at C, you'd be looking directly up at this feature. So that's the simplest geometry, and that's the one that I'm going to work with right now. A more complicated geometry is that if these 2 observers were located at different spots on the 2-dimensional plane that these triangles are sitting on. And I'm not going to do that problem because it's going to be way more complicated. But basically what we have here from these 2 observers is we have the distance d, they can measure that very carefully, and we have these 2 angles, alpha and beta, which they can measure very accurately. And with that information, it's amazing to think that we can determine what that height of the aurora is from these pieces of information. And here's how it all works. Let's look at triangle BCD. That's the innermost triangle. The tangent of beta, this angle beta, is the height of the aurora divided by the base length x. Okay, enough said. That defines what the tangent of beta is, and it defines what the angle beta is. Angle alpha, the tangent of that angle, is the hypotenuse h divided by, it is the height divided by d plus x. X, of course, is that base length between B and C that we don't know what that is. And we don't really care, but we don't know what that is. We do know what d is, so we have tangent alpha written in terms of the height, which we want, d, which we know, and x, which we don't know. And so that's what this triangle looks like, triangle AC and D, ACD. Now, what we can do is we can do a little bit of mathematical manipulation. So we put h on one side of this equation and d and tangent alpha on the other. Multiply both sides by d plus x and simplify, and you get the lower equation, which is h equals d times tangent alpha plus x times tangent alpha. Right, that's a little algebra. Now, the tangent beta is defined as the height divided by x. So x equals the height divided by tangent beta. Now what we can do in that previous equation, which had x in it, is we can eliminate x by replacing it by h divided by tangent beta. So now when you simplify all of this, what you wind up with is a very simple formula that only involves tangent alpha, tangent beta, and d, which is the distance that you do know. And then simplifying that further, putting h on one side and simplifying, here's what you get as the formula for the height of the aurora. It's d times tangent alpha tangent beta divided by tangent beta minus tangent alpha. I mean, you look at this equation and you say, who could ever have come up with an equation that looks as screwy as this? I mean, really, it does look very screwy. But it's the result of a systematic process of doing the geometry and the trigonometry. And provided you haven't made any errors, this is a very rock solid equation that's going to tell you what the height of that aurora is if you just know the two angles and the distance d. I find it absolutely amazing that you have eliminated the unknown that you don't know, which is x, and now have a very simple equation that just involves three numbers that you do know and measure. Can you reduce this even further so that it only involves one or two of these things instead of three? No, because as you saw from our scale model drawing, you definitely need three pieces of information in order to get this fourth piece of missing information from the properties of a triangle. Okay, let's plug in some numbers. If observer A measures the alpha angle of 35 degrees and observer B measures beta as 45, and D is 75 kilometers, you plug in the numbers and you get a height of H of 175 kilometers. I'm going to leave it up as a problem for you to find the missing length X, because there now is enough information to solve for X exactly. But the point is that this is a powerful method for using two observers measuring two angles who are separated by a fixed distance. And from this, you can measure the height of an aurora. So now, how high up is an aurora? Well, we know from a variety of other observations, much more accurate than what I've shown here, that typically auroras start at about 80 to 90 kilometers above the surface of the Earth. They never get closer to the surface of the Earth than that, because in order to essentially keep the oxygen atoms lit to produce the light we see, they can't be in an environment that has too much density. And of course, as you get closer to the Earth, the atmosphere becomes denser. And so the oxygen atoms really don't have enough time to emit the light before they get excited or collide with something else that then removes the energy by collisions instead of by emitting light. So there is a bottom to aurora. They really don't get closer to the surface of the Earth than about 80 kilometers or so. Do they ever reach the ground? No. They might appear to reach the ground, but you know, the eye sees all kinds of bizarre things, and we tend not to treat those as being real-world events. And the optical illusion that an aurora is somehow touching the tops of a mountain is very often a projection effect of a nearby mountain seen against a very distant aurora. Finally, can you hear an aurora? Well, there is absolutely nothing that you can hear that's 90 kilometers away with your ear. And the gas density of these aurora is so low that they don't produce enough pressure changes to reach the ground anyway. So there is no scientific reason why you should hear an aurora because there's no physical mechanism for any variations in pressure at the aurora altitudes to make it down to the surface of the Earth. Now, there are all sorts of inbuilt reasons why we think we hear sounds from aurora. Aurora look like fire in the sky, and we always associate fire with the crackling of something in a fireplace or on a log. So the mind is, I don't want to make this sound like we have an answer for everything, but the mind is extremely good at filling in information with its best guess of what's going on. The fact that you have a blind spot in your optical field that's completely black and has no receptors in it, you don't know that because the brain fills that part of your optical field in with a reasonable approximation of what it thinks the background should look like. So you never see this dark hole in your field of view 20 degrees away from the straight ahead direction that you're looking. Similarly, the mind fills in all kinds of other things too that go on around us that make the world look more like a continuous thing rather than a discontinuous series of jerks and changes. Similarly, for aurora are a phenomenon that you don't have access to on a day-to-day basis. Even if you live, if you're a native that lives up in the Arctic Circle, you don't have a ground-based access to the physics of aurora, at your campsite or in your living area or whatever. So your brain has absolutely no understanding of what it's expecting to see when it looks at an aurora. So it appears to be that what it does is it fills in the five senses experience of an aurora with a fictitious audio component, which has nothing to do with what the aurora is actually doing. All right. Similarly, you can't smell an aurora, and you can't touch an aurora, and you can't taste an aurora. So, it's very interesting the way the human mind adapts to missing information. But it's interesting how answering a simple question like how high up is an aurora through these various geometric and trigonometric means can actually give you an answer to some fairly interesting, human level questions. Okay, well, that's what I have to say today about aurora and citizen science. Next time, we're going to talk about the sun touches everything. Well, it certainly does, and the most common way that you know that it touches you is through its sunlight. Sunlight is a very valuable quantity. We're now discovering in order to become a green civilization, we have to avail ourselves more of how to convert sunlight into electricity. And so next time I'm going to talk a little bit about how that works and how satellites and spacecraft avail themselves of solar panels, as do many homes around the country, which are now sporting solar panels on their roofs. So that's it for today. And I'm going to stop sharing and return the program to Hillary.
Okay, thank you so much, Sten. This was great. I just wanted to go back and show you again the slide that has the information about where you can get a copy of this recording later today, and also the slide deck. So if you use the QR code on this slide, then it'll take you right there. And Sten gave you a sneak preview for January. It's January 16th. So sign up now. There's a link for you to register ahead of time at the bottom of the page. And then I think that's it. Yes. So if you will put in in this folder, we'll put the link to register for January, and then I'll set up the other links for the other months. But that'll always be available to you. So thank you again so much for listening, and hope you can use some of the activities with your audiences. Take care.